that's roughly how it works. And let's show you the project. And so this is, I'll show this very briefly. I won't have time to talk about this too much, but it runs a convolutional neural network. Then it runs exactly the same recurrent neural network I showed before, and that feeds into a model that's trying to predict the next LaTeX symbol. So instead of distribution over words, we have a distribution over symbols. And the results are pretty striking. You almost never generate the same LaTeX, but you almost always generate the same image. So on the top, we have the original. On the bottom, we have ours. You can see that the LaTeX is actually quite different. LaTeX is incredibly ambiguous, but you roughly get the same image out of the system. Okay. So any other questions about that? Yeah?
The example you just gave is a sort of way of saying, you can create the same meaning without using the same symbols,
yeah.
which is a natural language sentence. You can get the same meaning out of a sentence without using the same words.
That's right, yeah.
Do you have examples of doing that kind of stuff?
What's great about LaTeX is the meaning can be quantified as pixels. What's incredibly confusing about language is we don't have that, right? It's very hard to know whether two sentences mean the same thing, or even whether they have the same semantics. And our lovely Sam Bowman here at NYU actually studies this and has amazing kind of data sets to try to get at this question, but it's very challenging.
Because the follow-up to that is, I guess, I remember having a discussion in a similar round, which was that once you can do that, generate sentences that use different words but have the same meaning, basically plagiarism is an unsolvable problem. Because all our current plagiarism detectors rely on...
Let me put it this way. If we could write down the semantics of English, plagiarism would be the least of our concerns. Any other questions?
So the generated API could compile directly to the formulas. There weren't any errors.
That's right. That's crazy, right? I actually want to talk about that a little bit more about that in the next talk. Let's stick with that. This model can generate LaTeX that almost always compiles. We didn't constrain it at all. It saw enough LaTeX. It always seemed to generate LaTeX that compiled. I can't generate LaTeX that compiles every time. It's really hard. So I want to talk about that a little bit more. So I'm gonna. I have three actual technical parts of this talk. I'm probably only going to get to two of them at best, but I want to talk about the next part, which is pretty fun. Yeah.
You don't give the rules for LaTeX.
I don't know the rules for LaTeX. I don't know if anyone knows the rules for LaTeX. I don't know if there's a BNF grammar for LaTeX. I don't know. Maybe someone finds it. I couldn't find it online. I tried. It's really complicated. Yeah. Also, these are physics papers. They use all the crazy tech stuff. It's really, yeah. Okay, I want to go on though because I'm running really far behind. I want to show you the next part because it's pretty cool. So this is work by a postdoc I work with named Hendrik Strobel. He's a specialist in visualization. He came to my office one day and said, how do we go about looking at these models and trying to get a sense of what the heck is going on? How come they're so good at predicting the next symbol? So, I dropped the slide here. In Vision, they have incredibly great visualization for looking at how their deep learning models work. You should go online and look at some of the images they've generated from visual applications. They're amazing. They can look at how the models pick up on, say, the eye of a fish, or the nose of a dog, or like the curve of an intersection. It's very, very neat. We don't have that for text, and I'm so jealous. What we have is this. We have 100 or 1,000 dimensional vectors every time step of our model. There's no rhyme or reason to what they are. They're trying to capture an entire sentence in this vector, and we don't know what they're remembering. There has been some really cool work that looks at visualizing these systems, particularly this blog post by Andre Karpathy in 2015. In this model, the blue and green dots represent one dimension of this vector, and it's telling you what that dimension is looking for. Here, what you can see is that it's green or on when you're in a URL, and it's blue or off when you're not. and it's actually using that to try to predict the next symbol. So I'm going to make up first a very simple language. It's a finite state language. It consists of 7 symbols, open and close parentheses, 0, 1, 2, 3, 4. I'm going to sample from a random grammar of its language. It can open and close parentheses, and it can generate numbers randomly. But when it generates a number, it always has to be the number of currently open parentheses. So if there are 2 open, it can generate 2. If there are 3 open, it can generate 3. If there's 0, it can only generate 0. Got the idea? So here's what our tool looks like. So along horizontal axis of this graph, I have samples from this model. 0, open paren, 1, open paren, close paren, 0, 0, etc. What I'm showing in the time series is all 1,000 dimensions of my RNN over time. So they'll change every time they see a new symbol. And those lines at every time point have to remember everything they're going to need to try to predict the next symbol. Okay? So they look pretty crazy. But remember, this task is not that hard. In fact, there are only 3 things that can come up next, right? It's only a close or an open parenthesis or one number. But to get that number right, it has to have counted how many currently open parentheses there are. And it has to store that information entirely in these black lines. Okay. Now, over time, the lines stay roughly the same if they're seeing the same number. And stuff seems to change only when you see a paren. So what the tool allows us to do is to try to zoom in and look at a particular moment in time. So what I'm going to do here is I've highlighted one open parenthesis, and what I'm asking the model is to tell me which dimensions out of 1,000 were off, but then turned on upon seeing this open parenthesis. And it's telling me that there are 2 dimensions, 440 and 625, that have that property. And note that these ones go off immediately upon seeing a closed parenthesis afterwards. Okay? So the kind of hypothesis is that these dimensions are tracking the fact that we've seen a 4. If we've seen a 4, then we probably are either going to see a 4 next or maybe a closed parenthesis, right? And that can help us narrow down the space of possible next symbols. But if we go further along in time, we can find areas where there might not be a 4 at all. So here we have one where it never actually generates a 4. It just generates an open paren, and that line goes on, right? So actually what this is capturing is the fact that we've gone into having 4 open parentheses, and therefore that cell must be on to tell us what we can generate next, which is another 4. So in the simple system, it's really easy to find these states that are counting in the sense that they're remembering that how many parentheses are on and using that to make the next prediction. Okay? So it's a pretty simple idea, but note that this would be very hard to do in a model that could only look at the last, say, 2 or 3 symbols, because it wouldn't have the memory to kind of keep track of all this information. Okay. So that's the simple one. We have this tool online, and we have about 20 different models in it. Let's look at one that's a little more realistic. So here's one of children's books. So here we have the language modeling problem of trying to predict the next word in text of children's books. So all the books she read and all the pictures she painted would have been glad enough to be the mother of, etc. And things are a lot crazier. There's like lots of lines bouncing up and down all over the place. It's not easy to see when certain cells go on and when certain states go off. Language is a very complicated system. There's lots of different things that factor in what word's going to come next in this system. But what we can do is we can kind of do exactly the same process. So if we highlight, say, a little prince, we can find a bunch of cells that seem to be on. Cool. And what we did is we let the system, or we we coded into the system to match or do a search for all the other times that this model had seen similar cells on over a certain range. So these can be arbitrary phrases of different sizes. And we're searching over our whole corpus to try to find similar phrases for this model itself. So, and when we do this, this is what we find. So you see a little prince, a little hut, a small hut, a little old woman, a good temper, a burning torch, a strong hand, a little shower. So kind of very similar phrases in their structure. They're phrases where you'd imagine similar things would come after. And also, there are things that have similar things come before. So we have like of a little prince, in a little hut, in a strong room, upon a white horse. So these are kind of different aspects of language that this model wants to remember in order to make its predictions. And we can actually quantify that. So in natural language processing, we often like to utilize things like part-of-speech tags or syntactic structure to try to get a sense of what the underlying text is doing. And if we look at all of these phrases that were only matched by the model itself, they all probably have a very similar syntactic structure. So they all start with a preposition, they have a determiner, then they have some adjective, and then they have some noun, and then move on. This is kind of some quantification of what might be happening under the model. Let me show you one more. So this one is Java code. So here I took about all the Java files I could find. I trained a model to predict the next symbol after tokenization. So when you have import java.io.file, you can see there's one dimension that seems to be tracking every statement in Java and tracking when you have a semicolon. Similarly, we can look at, say, import java.io.file and find similar representations. So here you could imagine in your head, say, a model that is trying to do code completion. Given what it seems too far, how can it try to predict the next symbol? So here are all different kinds of import statements. But let's get back to our previous question. So why might we care to have a language model that's really good over a programming language? Why is that different than natural language? And I guess the answer is, well, if you want to generate code, it's very important that it be syntactically correct. But you can learn the syntax pretty well just from lots of examples of that code. So our model for LaTeX has to learn that when you have a begin equation, you have to have an end equation afterwards. And you can't have another end before that, right? But that can be learned by this type of information. You have a couple cells dedicated to tracking that property, and then very highly do not, or maybe very unlikely to generate a syntactically incorrect symbol coming up next. That's the kind of thing that would be very hard to do in a classical language model you can do with these recurrent languages. For the sake of my Dylan reference earlier, we also have a model trained over chords. I don't know what to do or make of this yet, but it's pretty fun. So here are just like chord progressions. One thing you see in the chord progression model is there are a ton of cells that just stay on for a very long period of time. So things in language or code, things kind of jump around or end pretty quickly. But we have a bunch of these states that remain on for an entire song. And we think they represent things like key or possibly other aspects of the song. It just gives you a sense of how different these natural or human languages are. Okay. So, Rahel, sure that we need 15 more minutes? Is that
20 minutes.
20 more minutes? Okay, great.
natural language and say transform it to first order predicate?
There has been. We refer to that as semantic parsing. One issue with that type of work is there's only maybe about 800 labeled examples in the world, and they're all somewhat artificial. I talked to one of the experts in this area a couple months ago, and he said they're looking for first order predicate-like things, so like SQL queries, because there's a lot of SQL queries in the world, so you could have a language of SQL queries that you do out there. Yeah. Any other questions? Yeah.
Logic textbooks are full of examples of this, aren't they?
I guess so.
I mean, there are exercises, there are solutions.
Yeah, I wonder though, I mean, take all the logic textbooks in the world, I bet you don't get to 2,000 examples.
Oh, I think it'd be a lot more than that.
Really?
Yes, many more than
I
that.
don't think that's true. Well,
Should try.
we can have a chat. Okay. Any other questions? Yeah.
Have you used the visualizer and things like that to sort of randomly, or not randomly rather, targeted deletion of nodes from the model to see whether your hunches are correct in some sense? If you think one dimension tracks semicolons cracking, how do you verify that?
Yeah, that's a great idea actually. We haven't tried it, but I think it would be very neat to try. Yeah, you could have that be interactive. Yeah, if I got rid of this one, multiple prediction chain.
But if you think this thing represents a particular learned concept, then you should see huge changes in behavior if you kill it.
Yep, I think that's right. And there are actually other kind of statistical tests you can do. Kind of, yeah, this is great for that type of stuff. Yeah. Cool. Yeah.
How many dimensions does it take to count the number of parentheses?
Yeah. So I can give you the minimal, but actually, that's actually a great transition. So I'm going to use that to go to the next part of the talk. So I'll get to that in a second. So really quickly, I'm skipping this work. It's really cool. It's by my grad student Sam Weissman. It's called Sequence Learning as Beam Search Acquisition. If you're interested in this stuff, check it out. Okay. What I'm going to talk about instead is work called sequence level knowledge distillation. This work is kind of spurred on by the fact that a lot of people are productionizing these systems. They want to utilize translation systems in real-life applications. But we found that there's a barrier. And the barrier is that they're really big. As I said earlier, the original paper was 4 by 1,000. There was a paper for French English translation that's 16 layers, 512 units each. And Google's published system is 8 layers, 1,000 units each. On top of this, you have to do what's called beam search, which I haven't talked about, to actually do translation. And then people often ensemble these things. You're running like 8 models in an ensemble. And so deployment is pretty challenging to say the least, particularly if you don't have massive GPUs or have built your own hardware just to do this fast, as Google has. So the work we were looking at was how you can make these models smaller. In the neural network literature, there are 2 types of ways that people make models smaller. One is by pruning. When you do pruning, we simply mean you eliminate dimensions that just have a low weight. So you have some criteria, you just drop everything that's below a certain weight. The other idea is a little crazier. It's called knowledge distillation, or on Halloween, it's called dark knowledge. The idea here is the following. You train a very big teacher model. Then you, as a post-processing step, train a student model that's much smaller to try to mimic the predictions of the teacher. And it's been shown that this can make much smaller student models that perform quite well. So formally, we're going to call our teacher model Q. So that's going to model the probability of the next word with a giant neural network. And we're going to try to learn a smaller student model P that's going to mimic the teacher. So in practice, we're going to train these models by minimizing negative log likelihood. We're just going to run backprop to learn our parameter weights, trying to make the training data have the highest probability. For the teacher model, we said it's Q. So, sorry, in knowledge distillation, we're going to, instead of trying to mimic the training data, we're going to, instead of doing that, we're going to try to mimic the teacher model. So our criteria is going to be instead to minimize cross-entropy with this giant model's probability. So if the teacher was very certain about the correct answer, then it's going to back off to roughly what we were doing previously. If the teacher is very uncertain, we're going to instead try to match, say, a uniform distribution as opposed to a distribution spiked on a given word choice. So this technique, here's what it looks like. So we originally trained our system to match the correct answers. Instead, we're going to train a bigger teacher model, and then we're going to train the student to try to mimic its predictions, so to make these distributions match those. Okay. Cool. So this idea worked very, very well in vision. We tried it out on translation, and it doesn't work that well at all. If you start with a 4 by 1,000 teacher model, you get a BLUS score of 19.5. So think of these scores as roughly on your test data, how many words, word pair, word triples, word quadruples did you match with the true data. When we go to 2 by 500, we drop 2 points, so to 17.6, which is a very big drop for these models. When we apply this word knowledge distillation, we get to about 17.7, so we don't see the same kind of increase in accuracy that people saw when they applied these to just straight classification tasks. You get a little bit of a jump when you go down to 2 by 300, but it's still nowhere near as good performance as the large model. Okay, so this is a little worrisome. It means that kind of naive approaches can't get us small translation models that are accurate. So we tried a different approach. We said, maybe the problem is that word knowledge distillation is trying to match the probability of the next prediction. But in practice, we'd really like to be modeling the entire translated sentence. The teacher model is going to get some input, and it's going to produce an entire output sequence, not just a single word at every time step. And you can think of the teacher model as giving you a distribution over the entire space of possible translations. The problem is that space is really large. There are going to be exponentially in length number of possible translations. And so if we wanted to really model that property, we'd have to do a sum over all possible translations and weight the probability that the student model gave to those translations by the probability the teacher model gave it. Okay. So this is kind of our hypothesis. We thought it was pretty reasonable. We weren't sure how to go about doing it. So we tried something pretty naive. Instead of actually doing this sum, we're going to approximate this exponentially sized distribution with a point estimate. We're going to take a single point estimate of this distribution from the teacher model. We'd really like to just take the mode of the distribution. But even finding the mode is really hard, because we have to do a max over this exponentially sized space. So instead, we're going to run kind of a variant of greedy search and try to find an approximate mode. And we're going to approximate that entire exponentially sized distribution with this approximate mode that was computed by this. Okay. This is kind of a little bit of a crazy thing to do. It seems very unlikely we're going to really be able to model the distribution that well. But what I can tell you is the following. These neural networks are very sure of themselves. They really, when they make a decision, they really like that decision. And in fact, they put a tremendous amount of their math, even on that single approximate mode. So in practice, we found that like 2 to 5% of the math could be found in the distribution just by running this process. Okay. So here's how it works. We run beam search with the teacher. We take the highest scoring output. We then train the student model on that prediction. So let me just talk through this one more time. It's a little weird. We train the teacher model on the training data. We then test the teacher model on the training data. That produces this output sequence. We then retrain our student model on that prediction. Okay. Translation is a really hard problem. So the model can't memorize the training data. So it doesn't just spit it back out to us. It actually produces a different sentence And that's the sentence we're going to be training on. Yeah.
How do you avoid overfitting
How do we avoid overfitting?
the training data?
How do we avoid overfitting?
Training, both networks on the training data.
Yep.
So if there are any biases of any sort on the training data, then wouldn't your model would overfit and then the student network would just learn overfitted results?
Yeah, so I think we're very careful not to overfit the teacher data. I haven't talked about it too much, but there's a bunch of ways people stop these models from overfitting. The main one is that it's called dropout. But the reason the teacher is able to perform so well, 19.7, is because it is not overfit. Yeah.
I don't know how to phrase this question, but so you start with a 2,000 node teacher model.
Yep.
And then you train, say, a 500 node student model.
Yep.
It sounds like what you're saying is, if you train the 500 node model on the original corpus,
Yep.
you get a worse result.
Much worse.
And so can you characterize why that happens? Like, what's the? It's kind of like you're taking information out of the corpus, right? You're somehow.
Well, the model doesn't have enough capacity to learn enough about language to perform well on this task. So it seems like it needs a 4 by 1,000 to be able to learn something that's good enough for this model. Yeah.
But it sounds like basically using that information, you train a 500 node
Oh, I see.
better on some data, some new corpus,
Yep.
than on the original corpus.
Yep.
Like, what happens between those two corpuses that makes the 500 node thing work better?
Work better. Okay, yeah, great question. So I don't have a great theory here, but I can conjecture a little bit. So one theory people have posited is that these models are pretty unstable to train, and it seems necessary to have kind of overcapacitated models in order to learn to begin with. Versus if you use a smaller model, you might get stuck in a worse local optima on the underlying objective. And so the theory is that once you've trained the teacher model though, and then you're training on this problem, it's an easier problem because the teacher has somehow smoothed over the difficult parts of the original problem. For translation, human translations are much more complicated than they need to be. And so there's a lot of kind of sharp corners these models can fit. And if they're using a lot of their capacity to model that, it's not really necessary for the final thing we're trying to do. That's one theory. Again, it's kind of a pretty handy. Yeah.
Is the random initialization of the student model, is it not random? Is it taken from the teacher model?
It's random.
Okay.
Yeah.
It's not learning anything within that certain state from the teacher model. It's just taking the output.
That's right. Just taking that. Yeah. Yeah. So the one issue is it's not totally clear how you go from 1,000 to 500. Like there's not a direct map, but you can imagine ways you can come up with that. Let me get to the punchline. Okay, so there's one other point I want to mention, which is that when people do knowledge distillation, they often do an interpolation of two distributions. They interpolate the one hot distribution that they got from the training data with the teacher distribution. So you're not just training on the teacher, you have a little bit of the original data as well. You mix them and train on that. So we wanted to try to mimic that at the sequence level. And so what we do is the following. We produce from the teacher model a k-best list of possible translations. And then we take from that list, instead of the highest scoring one, the one that was closest to the original training data. So it's one that still scores quite highly in the teacher distribution. So it still models a lot of that math, but it also is influenced by the actual human-generated training. We call that sequence-level interpolation. Okay. So here are our experiments. So we ran on a large English to German translation data set. We compared word knowledge distillation, the first thing I showed, with sequence knowledge distillation, and then finally with sequence interpolation. So what I'm going to show you now are, in these two columns, are the results of these models in terms of GLOS score. And I'm also going to show you two things that you may not be clear yet, but the way we actually do translations, we do search over target sentences. This is showing results from a green search, a search with beam size 1. And this is showing search with a larger beam, a beam of size 5. And we can see that to make the 4 by 1,000 model work, you have to use this larger beam. You have to do a little bit of search. And that's how we get to 19.5. Remember again that the student model gets to 17.6 by itself with no tricks. And if you do greedy search, you go all the way down to 14.7. Okay. Now, first we tried word knowledge distillation. We didn't see that much of a gain. And then we tried sequence knowledge distillation. And we saw two things. So one, you gain back a lot of what you've lost. So you get about 1.4 blue points back. But even cooler is you also do pretty well even when you're doing greedy search. So the interpretation here is you both seem to capture the original thing we were trying to do, which is you train a reasonably good model. But you also train a model that is kind of easier to do searches. So there's many fewer kind of bad paths the model can take that it needs to get out. So that was actually a pretty interesting aspect of this project. On top of that, when you run sequence interpolation, you get back to roughly where you were before, about 18.3 blue. Furthermore, you can run the same process on the teacher itself. So you retrain with the same size model, and you actually get a teeny bit of a gain. But you also get this same property where you can run the model in this greedy mode, where you're not doing